Hello everyone and welcome. My name is Luis Rivera and I'm from Team CALY. We're here to talk about our final presentation, but first, let's get to know the team a little bit. Team members include Yamil Gonzalez, Maria Marrero, Maria Novoa, and myself, Luis Rivera. We will start off with an introduction to the system, followed by the system's design and technical aspects, and finally, a conclusion summarizing the team's experience. Our client's project uses the biochemical methane potential bioassay. Basically, you have organic material being decomposed by microorganisms and they release gases in the process. Our client's main purpose is to find the most effective way to generate methane for a pigsty in CALY, Puerto Rico. There are many different ways and systems to perform BMP analysis, but our client focused on the design proposed by Bernhard Drosk. This system consists of 4 different phases: digestion process, unwanted gas filtration, methane confinement, and discharge water storage. The client improved Drosk's system and automated data collection. However, the problem with the current system is that it lacks data validation. This can lead to overheating, evaporation, and overflowing. All these raise safety concerns for the electrical system. In addition, the collected data would be made inaccurate due to not reading the actual experiment conditions during any possible mistake. Thus, the experiment material and data need to be discarded. CALY set out to create a logger monitoring system capable of performing the data collection process while implementing modular redundancy in the system's sensing module. Additionally, there is data duplicity by storing values in a remote database as well as a local SD card. The client will be able to monitor the data remotely via a custom web application. All documentation needed for replication, such as circuit schematics, bill of materials, and the code repository, is completely finished. These documents will be handed to the client, as well as all reports submitted in the course.
Milestones defined for this project included problem identification, which consisted on meeting with the client to understand his needs and gather requirements. System design, where we analyzed the alternatives available and selected the ones suitable for the project. Modular development, which consisted in the separate construction and testing of the different modules of the system. Modular integration, which was carried first hardware and software components alone, and then globally. Finally, system deployment, which consisted on assembling and uploading the project into its final destination for client approval. Human resources and fringe benefits is above expected due to overtime hours. Instead of working 25 hours max, members are working 28 hours on average. This goes over the 5-hour overtime limit established in our revised budget. Utilities and facilities remain unchanged. Equipment, materials, and workbench real cost is below calculated because the team was able to use an existing workbench and some equipment was already owned by the CALY members. Overall, total cost is about 14.52% over the calculated budget. For the system specifications, first, the system has to detect the temperature at the reactors and the water bath, and the volume at the burettes. This was obtained by using temperature sensors and pressure sensors. The system also has to maintain a uniform water bath temperature and discharge burettes when full. This was implemented by using solenoid bulbs, a water heater, and a water pump for circulation. The system has to store the collected data locally and remotely. This was obtained by using MQTT and Python OS libraries to create and to write to files. Finally, the data collection should be managed both locally and remotely. This was implemented by including an LCD screen along with push buttons and implementing a web page using tools such as JavaScript, HTML, Python, Flask, and others.
The design alternatives are divided between software and hardware. Our software areas are API, frontend, and database engine. For each, we have a couple of alternatives, and the selected are the following: Flask, React, and PostgreSQL, respectively, for the reasons stated on the screen. Continuing with the hardware design alternatives, the following table only show a few components of the system. For each, we have a couple of alternatives, and we selected the following: Raspberry Pi 4, DS18B20, transducer, GSO, and a 12-volt 8-amp adapter, respectively, for each of the reasons listed above. Moving on to the system architecture. Here, it is possible to see all the components that the system is made of and how they interact or communicate with each other. This is the setup of the prototype in the experiment table. We can see where some of the components are located. Here we have a better look of the condenser and it's possible to see the water pump. Now we have a better look at the reactors, the water bath, and the heater.
For a short demonstration, we are going to start data collection for an experiment. The sensors have already been calibrated. We are going to traverse the screens. This is the up, down, and enter buttons. So now we want to start the data collection process, and we're going to press enter. We're going to set the water bath temperature at the temperature we desire with the buttons. Now we are going to set it to 25. So now we see an overview of what each reactor is reading for both temperature and volume. Currently the burettes are empty, so that's why we have a very small amount of volume. The maximum amount is 50 milliliters. Now if we want to see other information while the experiment is running, if we press the enter button, and we can choose to pause the experiment, see a reactor breakdown for the experiment, or the water bath status. We're going to first see the water bath status right now, and the temperature is 25.4. We desire to have 25, so that's why the heater setting is currently on low. To exit, we press enter. And now we want to see a breakdown for the reactors. This is to see what each specific sensor is reading in case you want to identify a faulty one for both temperature and volume values. Now if we head back, and we can also pause the experiment, the data collection. You can either choose to resume now that it's paused, or to stop the data collection process, which is what we are going to proceed to do. We're going to confirm since this will not be open again, the experiment information. And now we can choose to start another experiment.
Welcome to the Hatch 497 web application. Let's quickly log in, and you can see a condensed station view with the most recent experiments. Now let's go to station 2, and we'll see the latest data readings as well as all the experiments tied to the station. We can start and pause data collection as well as stop the experiment completely. Now let's create a new experiment. We can input the random parameters such as the ones shown on screen, and then we can submit the information. Experiment successfully created, and it will be shown in the experiment table below. Now let's go to a specific experiment, say experiment 1, and we can see all the information from that experiment and edit it in case we made a mistake. I want to change cocoa to carrot. Submit, and that's great. We can see all the sensor readings with their transient and permanent faults, and we can graph that data in a nice little chart.
The project suffered difficulties due to the pandemic and the executive orders from the government. Also, there was a delay with the order of materials. The team did some adjustments, including daily meetings with status reports and extra hours working on the prototype. The project had positive impacts. Economically, BMP Logger is a cost-effective system. The environment was the most impacted since there's a reduction of excrement in bodies of water and organic waste of farms and food processing facilities. Also, these parties can use our prototype to transform their organic waste into biogas fuel. The scientific community is also impacted with a new option to perform bioassay. The deliverables will be available for the client to replicate our prototype. BMP Logger monitors and experiments and stores data local and remotely. The user can start, pause, or stop data collection. As mentioned, the project had positive impacts for the environment and society. The team achieved the development of a web application and logger in a short time frame. Besides pandemic, the delay of the order made the team to work extra hours and meet daily. CALY members learned to improve time management and the communication between peers. Also design a better work division to balance the workflow. It is projected to add multiple replicated stations to work together and improve some aspects of the logger and the web application. That concludes the presentation.